Why Earth isn't a perfect sphere. If you could hold Earth in your hands and spin it, the first thing you'd notice isn't the continents. It's that the planet doesn't roll smoothly. That's because Earth isn't a perfect sphere. It only pretends to be one when viewed from far away. Up close, scientifically close, it's lopsided, stretched, dented, and subtly misshapen in ways that tell the story of how the planet actually works. Let's break down why. The spin problem. Earth spins on its axis once every 24 hours, and that spin generates centrifugal force, an outward push that's strongest at the equator. The equator moves fastest because it has the farthest distance to travel in a single rotation, about 1,670 kilometers per hour. Meanwhile, the poles barely move at all. As the planet spins, centrifugal force pushes material outward at the equator, not dramatically, but constantly. Over billions of rotations, rock behaves less like rigid steel and more like slow-moving clay. The result is a bulge around the middle. If you measured the planet from the North Pole to the South Pole, you'd get about 12,714 kilometers. But if you measured across the equator, you'd get 12,756 kilometers. That's a 43-kilometer difference. Earth's equator bulges outward like a belt that's too tight. That alone disqualifies Earth from being a true sphere. This shape has a name, an oblate spheroid. If Earth didn't spin, gravity alone would pull it into a near-perfect sphere. But spin disrupts that balance, and the faster a planet rotates, the more pronounced the bulge becomes. Saturn, for example, spins so fast that its equatorial bulge is extreme, visibly flattened even through a telescope. Gravity isn't evenly distributed. If gravity were perfectly uniform, Earth might settle into a smoother shape. But gravity varies across the planet. Mountain ranges, dense rock formations, deep ocean trenches, these all pull gravitationally with slightly different strength. Over time, those variations tug Earth's surface up or down by measurable amounts. Mount Everest rises 8,849 meters above sea level. The Mariana Trench plunges 11,034 meters below. Compared to Earth's total diameter of over 12,000 kilometers, these features seem tiny, like scratches on a bowling ball. And it goes deeper than topography. Scientists map these gravitational differences using satellites, and the result is called the geoid, a model of Earth's shape based purely on gravity. The geoid looks bizarre. It's bumpy, with subtle hills and valleys that reflect mass distribution beneath the surface. In some places, the geoid is up to 100 meters higher or lower than a perfect ellipsoid. Imagine stretching a rubber sheet and placing uneven weights on it. The surface warps locally, even if the overall shape stays roundish. Earth's gravity field does the same thing, quietly sculpting the planet from the inside out. Earth's interior is in motion. Beneath the crust, Earth isn't solid in the way we think of solid objects. The mantle flows, slowly but continuously. Heat from the core drives convection currents that shift massive volumes of rock over millions of years. These movements rearrange mass inside the planet, which alters its shape from within. Glaciers grow and shrink, redistributing mass. Tectonic plates collide and pull apart. Ocean currents shift. Earthquakes release energy and rebound the crust. Even the Moon's gravity tugs on Earth, causing tides that temporarily stretch the planet's shape. Over geological timescales, Earth's rotation itself is slowing down, very gradually, thanks to tidal friction with the Moon. As the spin slows, the equatorial bulge will decrease. Millions of years from now, Earth will be slightly rounder than it is today. The poles don't line up perfectly. Even Earth's rotation axis isn't fixed. The planet experiences polar motion, where the geographic poles drift slightly over time. This isn't the same as axial tilt. It's the surface shifting relative to the spin axis. Melting ice sheets, moving water, and shifting rock masses all change how weight is distributed. Earth responds by wobbling, adjusting how it spins to conserve angular momentum. Think of a spinning top that subtly changes its balance mid-spin. The rotation continues, but the shape dictates how stable that rotation can be.
Oceans act like moving weights. Water doesn't stay put. Ocean currents, tides, and long-term sea level shifts constantly move trillions of tons of mass around the planet. That mass movement slightly deforms Earth's shape and alters its rotation speed by milliseconds. Even seasonal snow buildup in the northern hemisphere measurably changes Earth's moment of inertia. The planet is so finely balanced that weather and water leave fingerprints on its geometry. Earth isn't just squashed, it's uneven. Even calling Earth an oblate spheroid is an oversimplification. That term explains the equatorial bulge, but not the bumps. Earth has subtle high and low regions that don't align neatly with latitude or longitude. If you removed the oceans and exaggerated these distortions, Earth would look like a misshapen potato, not smooth, not symmetrical, but still clearly planetary. So Earth is squashed, bulging, and lumpy. Does it actually matter? Yes, especially for navigation, satellite technology, and understanding our planet. GPS satellites, for example, must account for Earth's true shape to give you accurate directions. If they assumed Earth was a perfect sphere, your location could be off by hundreds of meters. The satellite's orbit, based on the geoid and the ellipsoid model, constantly adjusting for gravitational variations and the equatorial bulge. Sea level isn't level either. Because gravity varies, ocean surfaces rise and fall slightly, depending on the mass beneath them. The Indian Ocean, for instance, has a natural depression in its geoid, causing sea level there to sit about 100 meters lower than it would over denser crust. Understanding Earth's shape also helps scientists study climate change, ice sheet movement, and tectonic activity. Satellites that measure Earth's gravitational field can detect when massive ice sheets melt, when groundwater is depleted, or when tectonic plates shift, all by tracking tiny changes in the planet's shape and gravity. Earth's imperfect shape isn't a flaw, it's evidence. It tells us the planet is active, that it spins, flows, shifts, and responds. A perfectly spherical Earth would be a dead one, motionless,
frozen in equilibrium. Instead, Earth wears its history in its shape. In the next episode, we'll explore another mystery of our planet, one that challenges how we see the world around us. Stay curious. The world is far stranger and more fascinating than it first appears.